Welcome to Fun Facts Online. Today, we are traveling to the very edge of time to discuss a discovery that is currently breaking our understanding of the universe. It is a story about the first light, impossible monsters, and a new class of celestial object that might just be the missing link in cosmic history. We are talking about the anomaly of the little red dots. When the James Webb Space Telescope, or JWST, first opened its golden hexagonal eyes to the cosmos in mid-2022, the astronomical community held its breath. They had a very specific expectation of what they would find in the deepest, oldest parts of the universe. Standard cosmological models predicted that as we looked further back in time, we would see the first galaxies. These were expected to be small, chaotic clumps of pristine, hot, young stars forming in the primordial hydrogen fog. Because young stars are hot, they burn blue. So the expectation was to see faint, blue smudges representing the fragile infancy of the cosmos. But the universe had a surprise waiting. Instead of just blue galaxies, JWST found something that simply should not have been there. Scattered across the deep fields, hidden among those faint smears of early galaxies, were hundreds of tiny, intense points of red light. These objects were compact, almost indistinguishable from stars to the casual observer. Yet, their redshift, a measure of how much their light has been stretched by the expansion of the universe, placed them merely 600 million to 1.5 billion years after the Big Bang. They were too red to be standard blue starbursts, and they were too small to be typical galaxies. To the instruments of Webb, however, they were screaming with energy. Astronomers have colloquially dubbed these objects little red dots, or LRDs, but do not let the cute name fool you. As the data began to be analyzed, a dramatic picture emerged. These were not merely red galaxies. They appear to be a missing link between the first stars and the monstrous supermassive black holes that anchor galaxies today. Some theories suggest they are Crimson Quasars, baby black holes shrouded in thick veils of dust. Others propose an even more radical idea, one that sounds like science fiction, that we are looking at black hole stars, or quasi-stars. These would be gigantic celestial objects where a black hole lives inside a massive star, eating it from the inside out. This discovery has sparked a crisis in cosmology. It challenges our understanding of how the universe grew up, and offers a potential solution to the long-standing impossible early black hole problem. It suggests that the monsters in the dark did not grow slowly over eons. They were born heavy, violent, and red. To understand why this is such a big deal, we have to look at how this discovery happened. It was accidental. It began with surveys like Eiger and Fresco, which were designed to map the distribution of galaxies and gas in the early universe to understand the epoch of reionization, the time when the first lights turned on and burned away the cosmic fog. Professor Jorrit Matthey at the Institute of Science and Technology Austria was among the first to notice a pattern. While analyzing images, his team found a specific population of objects that was being systematically misclassified. In previous observations by the Hubble Space Telescope, these objects were either invisible or just barely detectable faint smudges. But to JWST's near-infrared camera, they blazed with intensity. The confusion stemmed from their color. In astronomy, red usually signals one of two things: age or dust. Old stars are cool and red, while young stars are hot and blue. However, dust also scatters blue light, much like a sunset, making objects behind it appear redder. These little red dots were at redshifts that placed them when the universe was less than 1.5 billion years old. Simply put, there had not been enough time since the Big Bang for stars to grow old and turn red. Therefore, the redness had to come from dust, or a unique physical process. But here is the catch. If they were dusty galaxies, they should have been large, sprawling clouds of star formation. Instead, they were point sources. They were compact dots with radii often less than 100 parsecs, or roughly 300 light-years. For comparison, our Milky Way is 100,000 light-years across. These LRDs were pouring out the energy of a billion suns from a space smaller than a typical star cluster. This brings us to the core of the problem: the impossible monsters. For decades, astronomers have detected quasars, supermassive black holes actively feeding on gas at very high redshifts. Some of these quasars existed just 670 million years after the Big Bang and already possessed masses billions of times that of our Sun. This presents a paradox. In the standard model of black hole growth, a black hole starts as a seed, the remnant of a massive star, perhaps 10 to 100 times the mass of the Sun. This seed then eats gas to grow. But there is a physical speed limit to this feeding, known as the Eddington limit. If a black hole eats too fast, the radiation pressure from the superheated gas pushes away the food, choking the black hole. Even if a 100 solar mass seed ate at the maximum Eddington rate continuously for 670 million years, it could not reach a billion solar masses. It is mathematically impossible under standard constraints. As the text notes, it is like finding a kindergarten child who is 7 feet tall and weighs 300 pounds. The math of growth does not add up. Theorists propose two solutions. 1. Super Eddington accretion, meaning the black hole somehow broke the speed limit. 2. Heavy seeds, meaning the black holes did not start as stellar remnants, but started as massive seeds of 10,000 to 100,000 solar masses, formed by the direct collapse of giant gas clouds. The little red dots appear to be the smoking gun for these scenarios. Spectroscopy of the LRDs revealed broad H-alpha emission lines. In astrophysics, broad lines are a signature of gas moving at incredible speeds, thousands of kilometers per second. This happens in the extreme gravity well of a black hole. By measuring the width of these lines, astronomers estimated the mass of the central object. The results were shocking. The black holes inside these little red dots were massive, 10 million to 100 million solar masses, but they were residing in tiny, low-mass galaxies. In the local universe, a black hole is typically 0.1% of its galaxy's mass. In the LRDs, the black hole could be 10%, or even almost all of the mass. These were not galaxies with black holes, they were black holes wearing galaxies like a thin coat. Now, let's explore the most radical and fascinating explanation for these objects: the black hole star hypothesis. This idea gained traction after a team analyzed a specific, extreme LRD, nicknamed the Cliff. This object showed signs of a supermassive black hole, but lacked the X-ray emissions that should accompany such a monster. Standard active galactic nuclei are bright in X-rays because the inner accretion disk gets hot enough to emit them. The LRDs, however, are often X-ray quiet. Furthermore, the shape of the spectrum looked more like a star, a really weird red star. So what is a black hole star, or quasi-star? Imagine a cloud of pristine gas in the early universe, millions of times the mass of the Sun. Under gravity, it collapses. Usually this cloud would fragment into thousands of normal stars. But if the conditions are right, high temperature, and no heavy metals to cool the gas, it collapses into a single, monolithic object. The core of this cloud becomes so dense, it collapses directly into a black hole. But here is the key. The outer layers of the gas cloud are so massive that they do not blow away. The black hole is trapped inside the gas cloud. You end up with a hybrid object, a supermassive black hole at the center, surrounded by a massive envelope of gas. The black hole eats the gas from the inside. This accretion generates tremendous energy, which heats the outer gas envelope, causing it to swell and glow. To an outside observer, like JWST, you do not see the black hole or the accretion disk, you see the glowing outer shell. Because the shell is huge and relatively cool compared to an accretion disk, it glows red. It looks like a red supergiant star, but one that is millions of times brighter and larger than Betelgeuse. This hypothesis perfectly fits the LRD data. They are compact like stars, they are red because the envelope is cool. They have no X-rays because the thick gas envelope absorbs them, and they have broad emission lines because the gas inside is turbulent. If this hypothesis holds, the little red dots are snapshots of the universe's most violent gestation period, the moment when the first supermassive black hole seeds were being incubated inside giant cocoons of gas. There is also a complementary theory proposed by Fabio Pacucci regarding how these seeds form, known as the runaway collision scenario. In the dense core of an LRD, if it is composed of stars, they would be packed so tightly that they would undergo runaway collisions. A massive star collides with another, merging to become bigger. Its gravity increases, pulling in more stars. It grows exponentially, becoming a very massive star with a mass of 10,000 to 100,000 suns. This star is unstable. It lives fast and dies young, collapsing directly into a heavy seed black hole. This process takes less than 1 million years, effectively acting as a black hole nursery. Once the black hole forms and eats the remaining gas, it likely blows away the cocoon and reveals itself as a bright blue quasar, the type we have seen for decades. In this view, the LRDs are the cocoon phase of quasar evolution. Let's look at some specific case studies to see just how weird these objects are. First, there is the Cliff, at redshift 3.55. It is named for a dramatic drop in its spectrum called a Balmer break. Usually, a Balmer break indicates an old population of stars where hydrogen has been used up. But at this redshift, the galaxy should NT be old. The black hole star model explains this break not as age, but as the specific atmospheric signature of the dense gas envelope surrounding the black hole. The atmosphere of the black hole star mimics the chemistry of an old galaxy, fooling our standard tools. Then there is Kuiper's LRDZ9, found at redshift 9.288. This object exists just about 500 million years after the Big Bang. It is one of the furthest confirmed black holes. It hosts a broadline AGN, meaning the black hole is already churning gas at high speeds. Its existence so early pushes the heavy seed theory to the limit, implying that the process of forming massive black holes began almost immediately after the first stars turned on. Another fascinating object is A274445924. This is the brightest LRD found so far. Astronomers used ALMA, the Atacama Large Millimeter Array, to look for molecular gas like carbon monoxide, which usually fuels star formation. They found very little. This suggests the LRD is not a standard starburst galaxy. Instead, ALMA detected neutral atomic carbon, hinting at a harsh environment dominated by the radiation of the central black hole, disconnected from standard molecular clouds. One of the most engaging aspects of this mystery is how these objects deceived astronomers for so long. They exhibit what is called a V-shaped spectrum. In the ultraviolet, there's a faint blue glow, likely from scattered young stars in the host galaxy. Then there is a dip in visible light, followed by a rocket up in brightness in the infrared. Standard models tried to fit this as a dusty AGN, a blue quasar hidden behind red dust. But the math failed. To be that red from dust, the dust would have to be so thick it would block all the light. The black hole star model fixes this by suggesting the object is intrinsically red. It is a 5,000 degree Kelvin surface of a gas cloud light-years wide, powered by a black hole heart. A major piece of evidence supporting this is the X-ray weakness. The Chandra X-ray Observatory, which has been detecting black holes for 25 years, stared at the patches of sky containing LRDs and saw darkness. If these were standard supermassive black holes, they should be shining like beacons in X-ray. Their absence supports the cocoon theory. X-rays are high-energy photons, easily blocked by dense gas. We are not seeing the black hole directly. We are seeing the glowing cage that contains it, which absorbs the X-rays and re-emits them as infrared light. So, what does this mean for the history of our universe? It rewrites the timeline. The old timeline went from the Big Bang to the Dark Ages, to the first light seeds, to small black holes, which then slowly merged over billions of years. The new timeline implied by LRDs suggests that after the Dark Ages, huge gas clouds or dense clusters collapsed directly into heavy seeds of 10,000 plus solar masses. These seeds then grew rapidly inside gas cocoons, the LRD phase, hidden from view until JWST arrived. Eventually, they blew off their cocoons to become the blue quasars we see later, which then settled down to become today's supermassive black holes. The little red dots are essentially the teenage years of black holes, a phase of rapid, messy, obscured growth that we had never seen before because we lacked the infrared vision to pierce the red veil. The search is just beginning. The scientific community is mobilizing to verify the black hole star hypothesis. Future campaigns with ALMA will look for outflow signatures to see if these envelopes are expanding or rotating. Variability studies will watch these dots to see if they flicker, as chaotic accretion usually does, or if they remain stable like a star. And future telescopes like the Nancy Grace Roman Space Telescope will join the hunt. In conclusion, the little red dots are more than just a new entry in a catalog. They are universe breakers. They broke our star formation models, our black hole growth models, and our expectations of the early universe. We used to think the early universe was a place of small, blue, innocent beginnings. The Crimson Quasars reveal a darker, heavier truth, that monsters were born early, born big, and born in the heart of red, dusty cocoons. The little red dots are not little at all. They are the titans of the dawn, the heavy seeds from which the structure of our modern cosmos grew. As we stare at these crimson specks, we are witnessing the primal violence of creation. The golden eye of Webb has blinked, and in the darkness, it found 1,000 red eyes staring back. Thank you for listening to G Fun Facts Online.